Good afternoon, everyone. Good afternoon, everyone. Welcome back to the tutorial class. And okay, before we start, I'm going to take your attendance first. So just let me know if you're here, either through the message box or you just use your mic. Okay. Hing Dong, are you here? Hu Hing Dong? Hu Hing Dong? Lu Jui Min? All right. Ng Han Xiang? Ng Han Xiang? Okay. Ng Wei Hong? Good afternoon. Ong Mei Lin? Ong Mei Lin? Okay. Peng Shui Wen? Peng Shui Wen? Kwa Yihang. Oh, Peng Shui-wen is here. Kwa Yihang is here. So Yan Cheng. Okay. Tan Chin Shen. Okay. Teo Leong Ho. Teo Leong Ho. Teo Yi Si. Teo Yi Si. Wong Chung Yi. Wong Chung Yi. Good afternoon. Wong Ka Seng. All right. Yong Wing Liang. Okay. Yong Chi Ye. Okay. Good afternoon. All right. Hu Hing Dong, are you here? Hu Hing Dong. Hu Hing Dong. Okay. Good. Teo Leong Ho. Teo Leong Ho, Teo Yi Si. Teo Leong Ho and Teo Yi Si. 13. Okay, 2 is not here. All right, I'll check your attendance again later. Now, we are going to go through tutorial 4 today. So, tutorial 1 is on introduction to microcontrollers and embedded systems. We have gone through that. Tutorial 2 is on software development, programming lah. Tutorial 3 is on processor architecture and interrupts, right? So tutorial 4 is going to be on memory and the system control space, memory, okay? And as usual, I've already uploaded the tutorial and all the answers. So I just want to show you that the tutorial questions, again, are all theory questions. So you can find the answers in the textbook, right? These are not in the textbook, in the lecture notes or the textbook. You can find all the answers in the lecture notes or the textbook. Okay, for example, um, identify three types of memory. Three types of memory. So the three types of memory are you have device type, strongly ordered type, and normal type. You have three types: device, strongly ordered, and normal. So these three types of memory, they have different attributes: bufferable, shareable, cacheable, execute never, and access permission. So it's all different. Now, what the tutorial wants you to list is just the bufferable and cacheable attributes lah. So for example, strongly ordered is non-bufferable, non-cacheable. Okay, because strongly ordered memory type, this is your system registers. You know, this is your system register, strongly ordered. This is your system region. All your system control registers are here, system region. So the registers for your NVIC, SysTick timer, memory protection unit, all these registers are strongly ordered. Now, what does it mean? Strongly ordered. Buffer is non-bufferable and non-cacheable. Non-bufferable means you cannot buffer accesses to this region. Bufferable means the processor can write something to a buffer and then proceed without waiting for the write to complete. Okay, but strongly ordered, you cannot buffer because when you write to strongly ordered, it must be in a strict sequence. That means if your program says you write to this register, after that you write to this register, after that you write to this register. So it must follow this sequence. That's why it cannot be buffered. Okay, and of course, when you access registers, that cannot be cache, right? You see, the problem with cache is cache is now this is your processor. Your processor is really fast. This is your memory. For example, your SRAM. SRAM is slower than your processor. Okay, so your processor is really fast. So for example, let's say you have cache. You have cache here. Okay, you have cache here. Now, Uh, let's say, for example, your processor wants to access memory. So because memory is slower than the processor. Now I'm talking about, for example, is Cortex A. Cortex A, the processor can be a few times faster than your memory, right? A few hundred megahertz, clock speed. So the processor can be faster than memory. Now, if the processor is faster than memory, then whenever the processor accesses memory, SRAM, you have to wait for the thing to come, right? So a faster way is, let's say you got some frequently used data, very frequently used one. Then instead of accessing it from SRAM, the processor can copy this into the cache. And cache is as fast as the processor. So then when the processor access the stuff, the processor doesn't access it from SRAM, the processor will just, this is your processor call. It will just get it from cache. Now, what's the problem? The problem is that if the processor reads and writes from cache, then the processor is reading or updating the value in cache, not the actual value. This is just a copy. This is the actual value. So eventually, or periodically, the processor needs to write the value back to the underlying memory. We call this the underlying memory. So eventually, you have to write it back. Okay. Now, you think about this. If this is peripheral register, can you use cache? Cannot, right? Because if the processor wants to program the sysdig timer, for example, the processor must write to the peripheral register. It cannot write to cache. You write to cache, that means you're not doing anything to the actual hardware, right? So that's why strongly ordered is non-cacheable. Okay. Same with devices. Devices are your microcontroller peripherals. So your microcontroller peripherals also cannot be cached, but they can be buffered, right? They can be buffered because the sequence may not be important. Strongly ordered, the sequence is important. That's why it cannot be buffered. But peripherals, maybe the sequence is not so important, so you can buffer, right? Now, normal memory, normal memory, which is your code and data memory, you got two types, which is write through cache and write back cache. Now, write back cache is this one. This is write back cache. That means the processor will read and write from cache, and then periodically, maybe once every 100 milliseconds or once every 10 milliseconds, the value in cache will be written back to memory to update the memory. Periodically, cache is written back to memory to update it. Okay. Now, that one is write back. Right? Periodically, you will write back to memory. Write through means write through cache means whenever the CPU writes something to cache, the value will also be directly written back to memory. Okay, this is called write through cache. Whenever the CPU writes to cache, the value will also be written back into the underlying memory for writing. Reading the CPU just read from cache. The CPU doesn't read from memory to speed things up. Okay, so this just to explain bufferable and cacheable. Now, next question is just to show you another theory question. After that, we're going to do some exam type questions, some open book exam type questions. I'll just show you another theory question where you can easily find the answer from your lecture notes. Identify and describe six memory regions. Six memory regions. So the six memory regions are, like these six memory regions. You got your code region, SRAM, peripheral, external RAM, external peripheral, and system region. So these six regions have an address range. Each of them start from a certain address until a certain address. Okay, their size are all 512 MB. Right. RAM got two blocks of 512 MB. External RAM got two blocks of 512 MB or 1 GB. External peripherals also got two blocks of 512 MB or 1 GB. And then they all have different attributes, which is what you explain here. So identify and describe the six memory regions. You identify the six regions, the address range, and then you describe them. Okay, so the rest are all the same. They're all theory questions. Now, I want to let you do some, as usual, every week we are going to practice doing some exam type question. Okay, so this is an exam type question, right? Now, please take 20 minutes to do this, right? Please take 20 minutes. Please try this exam type question, right? And we will discuss at 4:30. Please take around 20 minutes to do this now. We will discuss at 4:30. Now, please try this really seriously. Please try this question really seriously because this is the type of questions that you will face in your final exam. And when you try out now, afterwards, we discuss the answer. You know how well you will do in the final exam. Okay? All right. So you can start now. All right. Okay, class. So it's 4:30, right? We're going to discuss this question now. Okay, everyone ready? Yeah. So you might want to print screen this question first, right? You can print screen this question if you want. Okay, so this is a standard exam type question. So standard exam type questions are 25 marks. Okay, but you notice that this is only 20 marks because we don't have part C, right? Your normal standard exam question, you got part A, part B, and part C. Part A is the direct question, very direct one, not difficult to do. Then part B is the more slightly more challenging, and then part C is the challenging question. Okay, so part A, if you understand what you have learned, you should be able to answer this question. So if you answer all four questions, part A, you answer the part A of all four questions, you will have no problem passing the exam. Okay, so you see, exam questions, exam papers, they are not designed to fail you and they are designed to pass you. So as long as you understand your classes and you understand what you have learned, you have no problem answering part A. I will show you shortly. Okay, now part B is a bit more difficult and part C is the more challenging one. So if you can answer part B, then you get a B, right? And if you can answer part A, if you can answer part C, then you get an A, right? So that's how we measure, we do our measurement. Okay, so let's look at this question. Now, you need to write a program segment. Program segment means you don't have to write the complete program, not the complete program, just a part of the program. So what do you need to do? You want to configure the memory protection unit to get this. Configure memory protection unit to get this. Now, what is this actually? What is this? You see your microcontroller, right? Your microcontrollers is like this. Wait, no. Okay. Your microcontroller's memory, right? Let's say this is your entire microcontroller memory. So it's a 32-bit microcontroller, 32-bit processor. So you can access 32 gig address space, 32 gigabytes, 32 billion bytes, 32 billion bytes. Okay, so in this entire memory space, 32 billion bytes, by default, by default, right? This part up here, this part up here, this part up here, 512 MB. This part up here is called the system region. Okay. Now the system region, this is where you have your NVIC registers, your SysTick registers, your MPU registers, etc. So these guys these are all the system control registers. So the system control registers they are very important. You shouldn't mess with them because if you mess with them, the whole system will crash, right? So how to avoid people messing with them? Then to access the system region, you uh, privilege privilege is required, right? To access privilege is required to access the system region. Okay, then you ask the question, what is privilege? Right? What is this privilege? Okay, so if you recall, you got your if you recall, you got your control register, right? Your control register in your CPU. Now your control register is 32 bits, but only bit 0 and bit 1 are implemented. The rest is not used. Okay, so what's bit 0 for? Bit 0 is to select the privilege level. Privilege level. So if it's 0, means privileged. Privileged means you got privilege. If it's 1, means no privilege. Okay, so what does this mean? If the control register bit 0, you put a 0 there. This is the default. This is the default. This is the default setting. So the default setting, 0, means you got privilege. You got privilege means you can access everything. You can access everything. But if the control register, you change bit 0 to a 1, the moment you change this, you set this bit to 1, it means now you got no privilege. No privilege means you cannot access this place anymore. And you also cannot change the control register anymore because the control register is a system control register. This guy is a processor register. So you cannot, once you go to no privilege, you cannot go back to privilege anymore already. Okay, so what's this used for? What is the control register used for? Okay, it's actually used in an operating system. So if you got no operating system, you don't really bother with this privilege. But if you got operating system, if you got operating system, right, then you got two types of code. You got the operating system is the OS lah. You got OS code, operating system code, and then you got thread code. Thread code, right? It's like now you have your PC in front of you. So your PC is running Windows. So the Windows program is your OS code. So the Windows program can access your entire memory, your DD-RAM lah. You know your computer got your RAM, right? Some of you got maybe 8 gigs of RAM. Some of you got maybe more powerful PC, you got 16 or 32 gigs of RAM. Maybe some of you, a lot of money, you buy 64 gig of RAM. Okay, so that is your system memory. Your operating system can access the entire system memory. But let's say now, you see now I'm running Paintbrush. Paintbrush is a program. This Paintbrush program has its own code and memory space. It cannot access the code and memory space of other programs, right? The Paintbrush program, it can only access its own code and memory space that it is allocated with. It cannot access, for example, the code and memory space of the PDF reader, you know. So each programmer has its own code and memory space. So similarly here, thread, thread, each thread has its own code and memory space, right? So the operating system is normally we give it privilege, while thread code has no privilege. We don't give it privilege. So thread code got no privilege, right? The thread code that can only access its own code and data space, right? Thread that can only access its own code and data space. Thread got no privilege. How you do that? How? Because by default, only the system region require privilege. Everything else don't require privilege. Whoa. So what if okay, what if I got this is here here is my thread 1. I got my thread 1 here. And then here I got my thread 2. Here I got my thread 2. So thread 1 I only let it access this part of memory. Thread 2 I only let it access this part of memory. How to do that? This is where the memory protection unit comes in. So when you use a memory protection unit, right, you can define okay, I can create a memory region. So this is called a MPU region. I can define an MPU region, this MPU region, and I can define up to 8 MPU regions, 0, 1, 2, 3, 4, 5, 6, 7. So let's say I call this MPU region 0, right? Then how do I specify this, define this region? First of all, I have to know what is the base address. What is the start address of this region? The base address. Okay. Then I have to know what is the size of this region. And finally, I want to set the attributes. Okay, I want to set the attributes. So first, I need to set the region number. Second, I need to set the base address. Number 3, I need to select the size. And number 4, I need to set the attributes. Okay, so this is how I can program this region. I can program this region such that thread 1 I can only access this region, cannot access other regions. How? By making only this region defined and others all is undefined. So you cannot access undefined. How we do that? Okay, step 1, step 2, step 3, step 4. Let's see how we do it. Okay, so we want to program the MPU, right? So we have to use the MPU registers, right? So step 1, you want to program the region, no? You use MPU region number register. Put in the value 0. Okay, done. So I've selected region 0. Step 2, base address. So what's the base address? Let's say the base address is 40,000. Let's say 40000 base address. Okay, let's say the base address is 4 uh, 4 not here, 40000. Okay, this is the base address. So MPU region base address register, give it the value 00040000. Done. Okay, next step, select the size and the attributes. So MPU region attribute and size register, RASR. So now we need to put a value. Now this is not so simple. This one we have to refer to the data sheet, size and attributes. Okay, let's look at the data sheet. But you don't have to go to the data sheet because I already put this inside here already. I already put this here, okay, in your lecture notes. All right. So okay, region attribute and size register. We got 32 bits, and all the bits got some function one. So okay, first thing we do, we need to enable this region. So bit 0, I need to set to 1 to enable this region. Bit 0, I need to enable. Okay, so what do we do? What do we do? Here, first of all, I put 1 left shift by 0. This one is the enable bit, or with this one to enable the region, right? Enable the region, I put 1 left shift by 0 to enable the region. Okay, next, what is the region size? What is the region size? Okay, what's my region size? Let's see. Let's see. Okay, let's say my region size is 256 KB. Let's say my region size is 256 KB. Okay, 256 KB. Let's say my size is 256 KB. Okay, 256 KB. Now let's see. 256 KB, 256 KB. The size 256 KB. The value is 10001. Okay, what's this value in decimal? This is a binary value, 2 power 0 plus 2 power 4. 2 power 0 plus 2 power 4. 1 plus 16. 1 plus 16. So this is 17. Okay. So I need to put 17 left shift by 1, right? 17 left shift by 1 because it starts at 1. So, okay. Next one is 17 left shift by 1. Okay. So this is to enable the region. This is to select 256 KB size. Okay, one more is the attribute. Now I need to set the attribute. Okay, what is the attribute? What's the attribute? What's the attribute? Okay, so thread code unprivileged. Thread code unprivileged. Thread code unprivileged. Let me write here. Okay, so my attributes is thread code unprivileged. Now, what can you guess from this? So thread code means that it is read only. Thread code code means is read only read only. Read only means you can only read, you cannot write because it's code. Code you cannot change it on. You read only. Unprivileged. Unprivileged means full access because privilege means only privileged can access. Unprivileged cannot. But if unprivileged can access, unprivileged can access means everyone can access. So this would be, in other words, we can say that this is full access, read only, full access read only, or unprivileged read only lah. Unprivileged read only. So let's find what is the setting for unprivileged read only. Okay. What is the setting for unprivileged read only? All right. So the access permission is starting from bit 24. Access permission is starting from bit 24. So I need to left shift by 24. What's the value? 24, 25, 26. 3 bits, 3 bits here. Okay, let's see the 3 bits. The 3 bits. What do I want? I want unprivileged read only. So unprivileged read only, this is privileged user access means unprivileged. So unprivileged read only, I got two possible values. I can use either 110 or 111. Okay. Unprivileged read only means privileged can also read only lah. Read only, privileged and unprivileged. Okay. So I can use 110 or 111, 6 or 7. Up to you lah. You want 6 or 7. So I take 6 lah. So I need 6 left shift by 24. 6 left shift by 24. Okay. So let's do it. 6 left shift by 24. And we are done. Okay. So we are done. This is for the first region. So okay, this is for the first region. No problem. Very straightforward. So now let's look at the question again. Let's look at the question. You got 6 regions, right? You got 6 regions. So we need to do it 6 times. Let's look at the answer. You need to do it 6 times. Okay. So first of all, you select region 0, set the base address and set the attribute and size. Then region 1, region 2, region 3, region 4, region 5. Okay. And then finally, once you are done, the last step is to enable the MPU. You need to enable the MPU. So control register, enable the MPU. Okay. So you see, I didn't use all these hash definer because the code is very simple. You don't need to use hash define. You can just put the value in directly. Right. So you see here, this is a region attribute and size register. Privileged read only, unprivileged read only. Left shift by access field. So access field is 24. Privileged read only, unprivileged read only is 6. So this is actually 6 left shift by 24. You can just write 6 left shift by 24. You don't need to write all these defined one. Don't complicate the thing. It's a very simple program. Okay. All right. So you can take a screenshot if you want. All right. So it's this is 12 marks. This is 12 marks. So 2 marks each. 6 regions. If you correctly define each region, that's 2 marks. So if you correctly define all 6 regions, that's 12 marks. See, very easy to get 12 marks. Right. Very direct. Okay. Now, once we are done with this, let's go to the next question. Next, let me go to part B now. Everyone okay? Okay, print screen already. Okay, so now I'm going to go to part B. Right? Okay, let's go to part B. Now let's look at part B. So part B says Cortex M0 or M1 uses von Neumann architecture, while Cortex M3, M4 uses Harvard architecture. What is the value of this arrangement? What's the value? What's the purpose? Okay, so let's talk about it. Now, you got CPU. This is your CPU, right? Now the CPU accesses. You got 2 types of memory. You got code memory. You got code memory and you got data memory. Okay. So the code memory is implemented using flash. Data memory is implemented using SRAM. They are just 2 different types of memory technology. The implementation is different, just 2 different types of memory technology. Okay, so if the CPU accesses code and data memory using a single bus, we call this von Neumann architecture. Right? You have learned this in the microprocessor subject, and you also learn this again in your computer architecture subject. Right? So it's the concept where the CPU can only access one code memory or data memory at one time, but cannot do both at the same time. So what is the good? What is the bad? Okay, the bad is lower performance. The bad is lower performance. Lower performance because you cannot do 2 things at the same time. So what's the good? The good is the circuit design of the CPU is simpler. The memory interface circuit, the design is simpler. So the processor is smaller and less complicated, right? So when it's smaller, it's cheaper, and it uses less power. That's the advantage. Okay. While on the other hand, the Harvard architecture, so it's designed in Harvard University, right? Von Neumann is a person. Harvard architecture is called after the design team, the computer science team in Harvard U that came up with this model. This is during 1960s, 1950s, 1960s. Okay, so I drew it wrongly. So it's two separate buses. Okay, so you got two separate buses to code and another bus to data. So you got two separate buses. We call this the Harvard architecture. What's the advantage? Advantage is you got higher performance. You can access both code and data at the same time. But disadvantage, CPU design is more complex. So it's more expensive and uses a bit more power. Okay. So if you look at the answer, right? So Cortex M cores with Harvard architecture, they have better performance, but the price to pay is power and area, more power, more area. On the other hand, the Cortex M cores with von Neumann architecture, right? You have reduced performance, but you got lower power and higher energy efficiency. Okay, so if you say Harvard architecture, better performance is 2 marks, but uh, worse area and power is 2 marks. Then if you say von Neumann is lower performance, 2 marks, but better energy efficiency, 2 marks. So 2, 2, 2, 2, add together 8 marks. Okay, so this is an open-ended question. You can write it in other ways as well. As long as your answer is logical, then you will get the marks. Okay, do you have any questions? I want to give you another exam type question to do now, but since we're out of time, we will straight away jump to the answer and look at the answer. Do you have any questions for this one? Everyone okay? No problems there. Okay, now let's move on to the next question. Let's move on to the next question. Right, so now you can print screen this. So this question is a SysTick timer. This question is on SysTick timer. So what do we want to use the SysTick timer for? Okay, you are now asked to write a program segment. Again, you're asked to write a program segment. So when we write programs, it's all in C. All your program is in C1. So I ask you to write a short C program segment. That means not complete program, just part of a program. To do what? Okay, to measure the number of clock cycles needed to execute a function. So I'm going to give you a function, then I ask you to measure how many clock cycles is required to execute this function. And we are going to use the SysTick timer for this. Okay, let's look at the answer. How do we do this? Let's look at the answer. How do we do this? Let's look at the answer. Okay, so I'm going to need some variables. I'm going to need one variable called start time, one variable called stop time. Okay, because I need to measure the start time and the stop time. Then the duration will be start time minus stop time, right? Start time, because this is a countdown timer. SysTick is counting downwards. So start time will be bigger than stop time. So start time minus stop time, I get my duration. Okay, so I'm gonna do something like this. I'm gonna do something like this. Okay, now you see, this is time. This is time. Okay, so at this point, I record start time. I record the start time at this point, right? Then this is the function. This is the function. Okay, so this one is the stop time. So when the function stop, then I measure the stop time. So then my duration is just equals to start time minus stop time. And you know lah, the SysTick timer is actually counting in CPU clock cycles, right? The SysTick timer is counting in CPU clock cycles one. So if I take the SysTick timer value, the start time minus the stop time, I'm going to get the duration of the function. I'm going to get the duration of the function in CPU cycles. Very nice, no problem, right? But now, what if, what if, what if the function takes, what if the function causes, the function causes the system timer to underflow. Okay, so what happens if here this is the function, this is the length of your function. The function is this long. This is the function. Okay, maybe wait, not so long, a bit shorter, maybe until here. Okay, this is the function, right? This is the function. So at this point here, at this point, the cystic underflow, cystic underflow. Okay, and then at this point, cystic underflow again. Underflow means cystic count to zero, count to zero, and then underflow. And then here, this is the stop time. This is the stop time. So now my question to you is, what is the duration? The duration is no longer just uh, the duration is no longer just the start time minus the stop time, right? So the duration now is, okay, we have to split it up. We have to split it up. Okay, so this part here, this part here is start time minus zero, because from start time all the way until cystic underflow count down to zero. So start time minus zero is start time lah. Right? Start time minus zero is the start time lah. Right? Plus with, okay, plus with, how about this part now? This part. This part will be, this part will be the reload value minus zero, right? Because when cystic underflow, you get reloaded, you get reloaded, count down to zero, reload value minus zero. So what is the reload value that we use? What is the reload value that we use? The reload value that we use is, we use the maximum reload value lah. FFF. We use the maximum reload value. FFF. Which is 2 power, which is 2 power 24. 2 power 24. Let me check. 2 power 24. Let me check. 2 power 24 is, yeah, 16 million, right? So the reload value is about 16 million. Okay, so I put it here. Put it here. So your reload value is equals to 2 power 24 lah. Reload value minus 0, 2 power 24. So plus with 2 power 24. Okay, and then this part would be, how about this part? So this part is the reload value minus stop time, which is the reload value is 2 power 24. Okay, so plus with 2 power 24 minus the stop time. Okay, so let's look at our code. Let's look at our code. Let's look at our code. Now, first we set our count to 0. First we set count to 0. Count is 0. What's count for? You see, a count is to count how many times we underflow. Count is to count how many times we underflow. So whenever the cystic handler runs, that means you got underflow lah. Right? Whenever you underflow, the cystic handler will run. So whenever the cystic handler runs, we just increment count. So by default, count is initialized to 0. Okay. Then we disable the cystic timer, give it maximum reload value, 2 power 24. And then we clear the current value to 0. Clear the current value to 0. Then we start the timer. We start the timer. Now, when you start the timer, it's going to start counting from 0. So 0 is going to underflow to the reload value. So here we wait for it to underflow. While the value is 0, we wait. Wait until it underflow and is reloaded. Once it's reloaded, then we record the current time. We record the current time of the sysdig. We record it into start time. So I got the start time already. Then I call the function. This is the function that I want to measure, processing whatever. Now, once the function finishes, then I record again the sysdig value into stop time. Okay. All right. Then I stop the timer. Now I want to get my duration. So if there is no underflow, the sysdig timer didn't underflow, count will be 0, and my duration is just a simple matter of start time minus stop time. Very simple, no problems. But if there is underflow, right, then I have to take into account how many times it underflowed. So I have to do this. I have to take start time plus with, okay, so what do I add? What do I add here? I need to take, so how many times I underflow? So I underflow one time, right? This is the first underflow. Then this one is the underflow number 2. So I underflow 2 times, right? So I should then take here, count minus 1. Count minus 1 multiply with 2 power 24. Because you see, if here I underflow one time, count will be 1 already. Then here I underflow one time, count will be 2. But I only need to multiply by 1. So I take count minus 1, multiply with 2 power 24. Okay. So my duration will be start time plus with count minus 1 times 2 power 24 plus with 2 power 24 minus stop time. Okay, which is what I get here. Right, this line. So if count is not equal 0, then I'm going to take, okay, this one got typo here. Let me correct the typo first. Let me correct the typo first. So we got a typo here. This one is not count. It is count minus 1. This one is count minus 1, right? This is count minus 1. Okay, so I put this back there. So the duration is start time, plus with count minus 1 multiply with 2 power 24. So count minus 1 multiply with 2 power 24 plus with 2 power 24 minus stop time. 2 power 24 minus stop time. Okay, so this is one way of doing it. Maybe you can come up with other ways to do it. I just show one way to do it. So, okay. Right, so I let you print screen the answer now. Okay, let me take this away. Or maybe you want this. Okay, maybe you want this. So I reduce the size. Put this over here. Let me put this down a bit. Let's put this here. Okay. So this is part A. How we can use the sysdig timer to measure the duration of a function in clock cycles. We can measure how long a function takes to execute in clock cycles using the sysdig timer like this. Yeah. So you just print screen this. Give you a few seconds. 5, 4, 3, 2, 1. Okay, done. Now let's look at part 2 of this question. Part 2, the more open-ended question. Okay, let's look at part 2 now. Okay, so part 2 asks you. The sysdig timer is a common timer across all Cortex-M devices. Cortex-M microcontroller. You see, your Cortex-M microcontroller, for example, the LPC1768, it has a sysdig timer. The STM32F also got a sysdig timer. The KL25Z microcontroller also got a sysdig timer. Because as long as you got a Cortex-M processor, inside the Cortex-M processor, you will have a sysdig timer. So can you tell me two importance of having sysdig timer as a common timer in all the microcontrollers? Okay, the important thing would be portability. Portability, because if you write code using the SysTick timer, then your code can run on different microcontrollers because all of them also got SysTick timer. Right? Okay, so let's have a look at the answer. Right. This is especially important for operating systems because operating systems, they spend a lot of time to write the code for operating system. So you want the code of the operating system to be easily ported from one microcontroller to another with minimal or no modifications. That is why we have the system timer. The system timer or the SysTick timer is actually specially included in the processor to support embedded operating systems. But of course, if you don't have an embedded OS, you can use the SysTick timer like a normal timer. It's a very simple, easy to use timer. Okay, so if you use it as a normal timer, the advantage is it has built-in security. It has built-in security because the timer is inside the processor core. So you need privilege to access it. And lastly, this SysTick timer is very suitable for low power applications. Okay, as compared to other microcontroller timers. Other microcontroller timers, they have a lot of features. They are very complex, so they consume a lot of power. So you need a timer just for some low power purpose. SysTick timer is the best. Okay, so I have here 3 points, or you can have any other logical answers. Why SysTick timer is a common timer across all microcontrollers. Okay, so you can print screen this if you want. All right, so we will stop here for today. Do you have any questions before we end the class, everyone? Do you have any questions? Okay, if no questions, what I want to say is, can you explain what is underflow again? Underflow is this. Underflow is this. You see, if I have a, let's say I got a 8-bit timer. Let's say I got an 8-bit timer. An 8-bit timer means the timer is 00000000 plus 1 becomes 1 plus 1 becomes 2 all the way until 11111111. So this is 0, this is 1, this is 2. Count all the way until 255. Dot 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 until 255. So 255, when you plus 1, what happens? We call this overflow. Overflow. Because your timer, you have an 8-bit timer. 8-bit timer means you got 8 flip-flops there. 8-bit timer. 8-bit timer. So when 1 plus 1, you're going to get 1, 0, 0, 0, 0, 0, 0, 0, 0. But this one is gone. Not enough space to contain it. So we will overflow back to 0. Underflow is the other way around. Underflow is if you decrement. So for underflow, we are talking about a down counter. So this one is an up counter. Up counter. So if I have a down counter means 11111111. I start with 255. So I have an 8-bit timer. Yours is 32-bit. I don't want to write so many ones. I just use an 8-bit example. So if you minus 1, count down by 1, you get 11111110. 254. Right? You minus 1, you get 1111 1011. 253. Right? Is that 253? Plus 1 is 100. 1 1 0 1. No, 101. This one should be 101. 253 is, sorry, 101. Okay, and then so and so on, dot dot dot, until you reach 0 0 0 0 0 0 0 1. Okay, then if you minus 1 again, you get 0 0 0 0 0 0 0 0. If you minus again, what happens? You're going to underflow here. We call this underflow. So this is a down counter. Down counter. So down counters will underflow, right? Up counters will overflow. Okay. Uh, so for the duration, count minus 1 is to consider when underflow occurs. The count minus 1 is here, here. You know, because you see, here I underflow 1 time, so the count will plus 1. At this point, count is equals to 0. At the first underflow, count is equals to 1. At the second underflow, count is equals to 2, right? But I can't take 2 times 2 power 24. That's wrong. I only need 1 times 2 power 24. That's why I take count minus 1. Okay? All right. That's why I take count minus 1. Is this okay? Now, if you don't want count minus 1, no, then you just initialize count to minus 1. No? Because we initialize count equals to 0. So the first underflow, it become 1. The second underflow, it became 2. Or if you don't want to use count minus 1, you can also say is equals to count multiply with 2 power 24 plus 2 power 24 minus stop time. So where did the minus 1 go to? It get absorbed by start time. Start time absorb the 1. Right? Because start time minus 0 is actually your reload value minus 0 is the same thing, man. Right or not? So instead of saying start time plus count minus 1, I can just write count times 2 power 24 plus same thing. We're just moving the numbers around. Right? We're just moving the numbers around. Is it okay? You can also write like this. If you take away the 1, so we absorb it, we use start time to absorb the 1. So it becomes like this. Same thing. Identical. Okay? All right. Okay, so class, now I'm going to give you exam type questions every week. So to get prepared, don't worry. Now is week 9. You still have 1 month before your final exam. And because the final exam questions are open book, it's not something that you can memorize in a few days before the exam. So you must start studying now. Right? You cannot wait until week 14. You must start studying now. Right? And how do you study? Just watch all the lecture videos, read all the lecture notes, and understand everything. Do your lab practical. So just 3 things. Just 3 things. Watch the lecture videos. That's number 1. Watch the lecture videos. Number 2 is read the lecture notes. And number 3 is do your lab practical. Number 3 is do your lab practical. Just do 3 things. Watch all your lecture videos, read all your lecture notes, and do all your lab practicals. Make sure you understand everything. And you are prepared to answer the final exam questions. So if you have anything that you don't understand, you want to clarify, just let me know. And I'll give you a better explanation of it. Right? Now, if you want more, after you watch all the lecture videos, you read all the notes, you do all the labs already, no problem at all. You want more, so you can read the textbook. This is a very, very nice textbook. It's the main textbook that people use when they are doing Cortex-M processor. They are studying Cortex-M architecture. This book is very, very, very good. Okay, it's in your library, right? I pointed it out to you before. I just point out again. This book, right? This book. Let me copy this and I paste it here. Okay, Trevor Martin, Designer's Guide to Cortex-M Processor Family. Second edition, first edition, same one. Same one, no difference. Okay, for what we are concerned, what we are learning, first and second edition, totally no difference. You can get this from the library. Okay, it's an ebook. You can get it from the library, right? So if you read the textbook and you understand, you have no problem, totally no problem getting an A for the exam. Totally no problem. The important thing I want to stress, and I keep stressing again, is understanding, right? We have open book exam. Open book exam means you can refer to internet, you can refer to books. You just cannot talk to another person. You can refer to anything. But even if you can refer to everything, but if you don't have the understanding, you cannot answer the question, right? As you have seen in the the, the past few exam type questions that I've let you try out. Okay, so today, start doing your revision. Start doing your revision today. Next week, I'm going to give you some more exam type questions to do. Right? Okay. Um, uh, and let's see. What am I giving you next week? So next week will be okay. I've uploaded tutorial 5 already. I've uploaded tutorial 5. Okay, so the exam type questions next week will be on the RTOS. Okay, the exam type questions next week will be on RTOS. So tutorial 5, again, these are all just theory questions from your lecture notes. No problem to answer one. So I will give you some exam type question in our next tutorial 2 weeks from now. The topic will be on RTOS. So try to prepare for it. Okay. Right. So if no questions, then we will stop here for today and have a nice weekend, everyone. Okay. Welcome. You're all welcome. Okay. Bye, everyone.